In this video, we're going to take a look at the binomial distribution. And to be binomial, the following four things must be true. First, there has to be two possible outcomes: success or failure, a fixed number of trials. Each trial must be independent, and the probability of success, doesn't change within each individual trial. So, two examples that we've seen in class we talked about. We flip 10 coins to 1. There's two outcomes, right? Heads or tails. Here, there's a fixed number of trials at n equals 10. If you think about coins, each coin, if you flip one coin, it's not going to affect the next coin. So each coin is independent. And then finally, the probability of success, if I call heads my success, the probability of heads will always be 0.5. It will not change, right? The 6 monkey scooters in a box that we looked at, well, there were two possible outcomes. It could be defective or it could work. Here, there's a set number of scooters in the box, n equals 6. Each scooter is independent of the previous scooter that you pull out of the box, right? Just because one works doesn't mean the next one will. Vice versa. If one is broken, that doesn't mean the next one is broken. So each scooter is independent. And finally, if you think back, if you can remember, the probability that we got a defective scooter was 0.4. That's because 40% of the scooters didn't work. That didn't change depending upon the situation. A game that a lot of us know from the beloved game show Price is Right is Plinko. And Plinko is actually a binomial setting. You think about it, as people drop the chips in and try to get different amounts of money, each time it works its way through the board, there's two possible outcomes. Either the chip goes left or right. And here it can go left or right. At this level, each level it's going to hit a peg and it has to make a left or right turn. So there are 6 trials, regardless of which way you go. Here we ended up in F. But if you look at it, even if we ended up at A, you'd have to go through 1, 2, 3, 4, 5, 6. At that point, it'd be left turns, right? So each time it'll bounce off of 6 pegs as it goes through this particular board. Each peg is independent. Just because it bounces right off the first peg doesn't mean that it has to bounce right off the second peg. And then finally, the probability of the success, if we want to call right success, it doesn't change. There's always a 50-50 shot that it goes left or right. Another example, you're a 75% penalty shot taker. So what's the probability you make 5 or fewer? Now, this is where we've actually kind of done this before. We said, all right, we'll let X equal, number of shots made. And we would set up those tables. And so sometimes we were given probabilities, like if you think about the insurance problem we did, where 1 out of 2,000 and 1 out of 500. Sometimes we can kind of think through, all right, a family wants to have kids until they have a girl. So we can kind of think through all the possible combinations. And then we also saw situations like this, where we set up the big chart, where we said, okay, here's X, here's probability of X. So in the next, 9 shots, I could make 0, 1, 2, 3, so on and so forth, right? And then what we've been learning is how to actually use the calculator to get in here and get those values. So one of the tricks that I started to show you, and we're going to look at it more in depth in this video, was that binomial CDF and binomial PDF. Well, in order to use that, the question we got to answer first, is it binomial? So go through the steps. First, there's 2 outcomes, right? Either make a shot, right? Either make or you miss. So there's your 2 outcomes. You got a set number of trials. You're going to take 9 shots. 1 shot doesn't affect the next. And then you're a 75% shooter, so you got a 75% chance of making it each time. So at that point, right, then we could define X, kind of like I did right at the beginning. X is making a penalty shot. And then we could set up our table, find the probabilities, and go. But since we know it's binomial, and I showed you this trick, we kind of introduced it at one point, this opens up the door to using that binomial PDF distribution in the calculator. Another type of setting that I'm going to touch on very quickly is geometric. And a lot of it's very similar. There's still 2 outcomes. The probability of success does not change. Each observation is independent. However, we're no longer setting, right? It's no longer a set number of trials. We're going until we get success, right? So the only difference between binomial and geometric is this one right here. Instead of a set number of trials, we're going until success. We've seen that in class with, right, they're going to have kids until a girl, and then they stop. We saw we'd roll the dice until we got a 6. We'll flip a coin until you get heads, and then you'd stop. You throw a dart until you pop a balloon, right? So we've seen this in class, and they're actually pretty straightforward to do. Here's one on the leeward side of Oahu in Hawaii. 80% of the residents are native Hawaiian. So suppose you fly there. What's the probability the first villager you meet is Hawaiian? What's the probability you don't meet a Hawaiian villager until the second, right? So here we go, until, right? If you start seeing the word until, that's what we're talking about something that's geometric, right? So go through the checklist real quick. One, there's 2 outcomes, Hawaiian or not, right? The probability that they are Hawaiian isn't going to change. 80% of the people are there. Each person's independent. If you think about it, just because the first person you meet is Hawaiian doesn't mean the second person has to be. And then finally, we are going until success, right? Even at the very beginning, what's probably the first person you meet is Hawaiian. So that's geometric. We're stopping once we meet that Hawaiian. Assume the probability you make a sales call on any given telephone call is just under 20%. So find the probability you make a first sale on the 5th call, first sale on the 1st, 2nd, or 3rd call. Do not make a sale on the first 3 calls. So is this geometric? So go through the list, right? Are there 2 outcomes? Either make a sale or you don't. The probability of a sale, 0.19. Each call, just because you make a sale on call 1 doesn't mean you have to make a sale on call 2. So each call is independent. And according to the question, make your first sale on the 5th call, first sale on the 1st, 2nd, or 3rd call. Do not make a sale on the first 3 calls. So this is all of a sudden saying, we make a sale on the 4th call or 5th call or 6th call. Here we go. We're going until we have success. So yes, this is a geometric example. So if I pull up the calculator real quick and I go into my distribution menu, a lot of times too, guys, instead of scrolling all the way down, if you press up, all of a sudden you see right here, you got geometric, PDF, and CDF just below your binomial. So we can actually use the calculator for some of these geometric distributions too. Although a lot of them are pretty straightforward and pretty simple to do by hand, in order to properly use the calculator. First, we got to figure out, is it binomial? Is it geometric? If it's not one of these 2 things, we can't use that function in the calculator. Next up, is it a CDF or PDF situation? So really, if you remember, CDF, we're going to call that continuous. And that's where all of a sudden you had probability X is less than or equal to, probability X is greater than, probability X is less than. And PDF, although this isn't exactly what that's where we just had probability X equals some kind of number. All right, so continuous and particular. Technically, that's not what those mean. All right, so what you'll know is that CDF for us, I'll take those things off, we'll always use less than or equal to. So for us, we could end up with a less than, a greater than or equal to, and we're going to just have to play some tricks. You guys have enough of a knowledge of what you're doing to actually be able to kind of pick through this pretty quickly. So let's pretend we got this chart and it's going on and on forever. They're on, past 5. So let's say that the problem dictates that we're doing less than 5. So less than 5, that would be everything from here and back. So less than 5 would be the same thing as probability X is less than or equal to 4. So this is the one that we'd have to use. We'd have to use 4 in our CDF situation. Let's say we did greater than 4. Well, greater than 4 would be everything from here, from 5 and up. Well, again, the calculator only does less than or equal to, so we could do 1 minus probability x is less than or equal to 4, and that gives us everything bigger than 4, right? We can use our complement rule. Let's say we want to go greater than or equal to 3, so I think about greater than or equal to 3 would be everything from including 3 and up this way. Well, again, the calculator only shades down. So for us, if we want to figure out this total area, we could just do 1 minus the probability x is less than or equal to 2. And about the only way that we get really proficient with this is just to practice it. But again, I will draw a chart like that pretty much every time I'm doing a lot of these problems just to make sure that I'm plugging the right number into my probability statement, because that's what I need for the syntax of the calculator, right? That's what we need if we're doing binomial PDF or CDF. We need to know that X. That's why this is so important. Regardless of if this is PDF or CDF, we need the number of trials for binomial, right? So they'll tell you, you're going to flip a coin 10 times. You're going to get 6 things out of the box. You're going to take 9 penalty shots. The probability of success, whatever they're defining success as, and then the X. Again, this is why setting up here, right, the original X isn't actually what we ended up using, except in one particular case. We got to think, what is it we need, especially with CDF, right? With CDF, so that we put the right number in right here. And then for geometric, it's just the probability of success and your X value. Again, that's why thinking through this situation, CDF always using less than or equal to, it's important that we set up the right probability statement. And then, this should say it has no set number of trials. And that's why all of a sudden we drop that first piece in the geometric CDF or PDF situation. We just worry about the probability of success and the X value. So let's look at a couple quick examples and be done with this one. So 96% of batteries will make it to their reported life and beyond. So in a batch of 10 batteries. So again, they either work or they don't work. N equals 10 here. Each battery independent. And then the probability that it works isn't going to change. It's 0.96. So the fact that we have a set number of trials tells me this is binomial. So the first thing I would do, write a quick probability statement. Exactly 8 batteries. So we're looking for the probability that x equals 8. So 1, I know that this is binomial. The fact that this is equals, it tells me it's PDF. And then so as I go to the calculator, again, first things first, set number of trials. So we're doing 10 trials. The probability of success is 0.96. And then I'm interested in 8. And the answer there is 0.052. Here, at least 7. So probability x is greater than or equal to 7. Again, it's binomial. But this time it's CDF. Now remember, CDF only does less than or equal to, so I got to think for just a second. If this is my chart, I'm going through and all of a sudden I go 5, 6, 7, 8, 9. If I want greater than or equal to 7, that would be the same thing as 1 minus x is less than or equal to 6. So now all of a sudden, I'm going to do 1 minus binomial 10.96, and now I know what my actual value of x should be, 6. And that's 0.9996. No more than 6, so that'd be the probability that x is less than or equal to 6. That works well because, again, we know it's binomial. We know it's continuous. And the fact that we've already got less than or equal to sitting there means it's pretty straightforward. 10.966, and this one is 0.0004. Here's back to our Hawaiian thing. So again, 2 outcomes. They're either Hawaiian or they're not. Each person independent. The probability of a Hawaiian is 0.8. But here all of a sudden, what's probably the first Hawaiian is the third person you meet. That you don't meet one until 3 people. That you don't meet one until after the second. So now listen, we're going until success. Which means now we're in a geometric setting. So the probability, the first one is number 3. Okay. So that'd be a geometric PDF in particular, 0.8, comma 3. And that would be 0.032. Now again, this is one we could probably do by hand. That means it's not a Hawaiian, not a Hawaiian. Hawaiian, which would be 0.2, 0.2, 0.8, and that gives us the same thing. But where geometric PDF and CDF comes in pretty handy is all of a sudden when you start doing inequality. So the first Hawaiian is within 3 people. So that means that you're going to meet one in less than or equal to 3 people. So now we're talking about geometric CDF 0.8, comma 3. That would be 0.992. If you want to do this a long way, you'd have to say, okay, it could be a Hawaiian first, or it could be not Hawaiian, or not finally Hawaiian. So this would take a little bit longer than actually recognizing. The calculator can do that, of course, pretty quickly. And then what's the probability you meet your first native after the second person? So that'd be the probability that x is greater than 2. So again, this would be geometric CDF. I know it's 0.8, but this is one of those you got to be very careful with. I'll just think about my chart up here. Yeah, I've been doing this for a few years, and I'll still sit here and draw the chart, or at least like a chunk of the chart, just to make sure I pick the right x value. So greater than 2 would be everything from 3 and up. Right? So that's the same thing as 1 minus the probability x is less than or equal to 2. So now when I go to the calculator, I do 1 minus geometric CDF 0.8, comma 2, and that's 0.04.